Imagine discovering that your grandmother was born 3 years before her own mother. Not metaphorically. The actual dates don't line up. The birth certificate says one thing, family records say another, and suddenly the timeline of your family history has developed an impossible knot that shouldn't exist. Now imagine that instead of a family tree, we're talking about the universe itself. And instead of a grandmother, we're talking about a star that appeared, for a time, to be older than the cosmos that birthed it. Hello, and welcome to the Sleepy Astronomer. Tonight, we're going to explore one of the most beautiful paradoxes in modern astronomy, a star called Methuselah that challenged our measurements, questioned our models, and forced astronomers to reckon with the limits of precision itself. For years, the numbers simply didn't work. This ancient star, still burning in the constellation Libra just 190 light-years from Earth, seemed to predate the Big Bang, which is, as you might imagine, rather difficult to explain. If you're settling in for the first time, welcome to these gentle explorations of cosmic mysteries. And if you've drifted with me before through deep time and distant stars, it's wonderful to have you back for another journey. If these peaceful wanderings through space and time bring you comfort or curiosity, don't forget to subscribe so you don't miss the next journey into the cosmos. And if this paradox intrigues you, how a star could seem to break the timeline of existence, a gentle light helps others find their way to these nocturnal wanderings about the cosmos. Here's what makes this story so compelling. It's not about bad science or mistaken observations. The astronomers who discovered this paradox weren't wrong to be confused. They were doing everything right. They measured the star's distance with extraordinary precision. They analyzed its light, decoded its chemical composition, tracked its motion across the sky. They used our best theories of stellar evolution, our most refined models of how stars age and die. And when they calculated how long this star had been burning, the number they got was impossible. 14.5 billion years old. Perhaps a bit less, perhaps a bit more, but hovering right around that number. The universe, according to our most precise measurements, is 13.8 billion years old. The margins didn't overlap. At face value, this star, HD 140283, the Methuselah star, would have to have formed 700 million years before time itself began. So, take a deep breath. Let your mind settle. And get comfortable, because tonight we're visiting a star so old it almost broke the laws of physics. A star that has witnessed nearly the entire history of the universe. A star that, for a brief moment in astronomical history, seemed to whisper a secret from before time began. Before we can understand how a star might appear to break the timeline of cosmic history, we should probably meet it properly. HD 140283. That's its official designation, about as romantic as a serial number on a refrigerator. Astronomers aren't always known for their poetic naming conventions, but this particular refrigerator has been around for 13 billion years, so perhaps it's earned the right to a more memorable title. And it has one, Methuselah, after the biblical figure who supposedly lived 969 years. Which in fairness is impressive for a human, but rather modest for a star that's been burning since before Earth existed. You'll find it in the constellation Libra, visible from Earth's southern hemisphere if you have a decent telescope and a bit of patience. It sits at apparent magnitude 7.2, which means it's just below what your naked eye can see. Almost visible, but not quite. Rather fitting for a star that spent so long hiding in plain sight before anyone realized how extraordinary it was. Here's something remarkable. It's only about 190 light-years away. In cosmic terms, that's practically next door. You could, in theory, with enough time and a spacecraft that doesn't exist yet actually reach it. This impossibly ancient object isn't some distant abstraction at the edge of the observable universe. It's here, in our local neighbourhood, close enough that we can study it in exquisite detail. Close enough to create a paradox. And it's moving. Fast. 800,000 kilometres per hour relative to our solar system, which is about the speed you travel if you are really, truly late for an appointment. It's streaking through space on an orbit that doesn't quite belong to the Milky Way's main disk. High velocity, eccentric path, not gravitationally bound to the orderly rotation of younger stars like our Sun. It's a wanderer, possibly a refugee from a smaller galaxy that was shredded and absorbed billions of years ago. Think about that for a moment. This star might not even be originally from our galaxy. It could be an exile, a survivor from a dwarf galaxy long since torn apart by the Milky Way's gravity, its former companions scattered or consumed, itself now drifting through a galaxy that wasn't its home. There's something quietly melancholic about that. An ancient traveller, moving through space that remembers nothing of where it came from. But here's what makes Methuselah truly special, beyond its age and its lonely orbit. It's still burning. Not in some faded, half-dead state, but actively fusing hydrogen in its core, generating light and energy the way stars do. After 13 billion years, after watching galaxies form and collide and die, after existing through nearly the entire history of the universe, it's still here, still patient, still glowing. It won't burn forever, of course, nothing does. But for now, Methuselah endures, and from 190 light-years away, its ancient light reaches Earth, carrying information encoded in photons that left its surface before humans existed. Before dinosaurs existed, before Earth itself had cooled enough to have oceans. We are looking at light from deep time, and that light is about to tell us a story that doesn't quite make sense. So, we have a star, ancient, fast-moving, close enough to study. But what makes astronomers look at this particular point of light and realize they're seeing something extraordinary? The answer is written in its chemistry, or more precisely in what's missing from its chemistry. Methuselah is what astronomers call a population 2 star, second-generation stellar populations, if you're keeping track of cosmic lineages. And it has extraordinarily low metallicity. Now, before you picture a star made of iron or copper, we should clarify something that drives chemistry teachers slightly mad. In astronomy, everything heavier than helium is called a metal. Carbon, metal. Oxygen, metal. Silicon, nitrogen, calcium, all metals. It's a gloriously imprecise system that makes perfect sense if you're an astronomer, and absolutely none if you're anyone else. Methuselah's metallicity is roughly 1/250th of the Sun's. Let that sink in for a moment. If the Sun is a rich stew of elements forged in previous generations of stars, Methuselah is, well, it's nearly just hydrogen and helium with the faintest whisper of anything else. It's chemically pristine, almost primordial. This matters because stars are cosmic historians. They carry the chemical signature of when and where they formed. The early universe, fresh from the Big Bang, was about 75% hydrogen, 25% helium, and trace amounts of lithium. That's it. No carbon to build life, no oxygen to breathe, no iron to make planets, or, frankly, anything interesting at all. Just the simplest elements, forged in the first few minutes after time began. Heavy elements only come from stars. They're manufactured in stellar cores through nuclear fusion, then scattered across space when those stars die, sometimes gently as planetary nebulae, sometimes spectacularly as supernova. each generation of stars enriches the cosmic gas a little more. The universe gets progressively more chemically complex over time, like a soup that's been simmering for billions of years, getting richer with each ingredient added. Methuselah's chemistry tells us it formed from gas that had barely been touched by previous stellar generations. Almost pure primordial composition, which means it must have formed very, very early, soon after the first stars died, and scattered their sparse offerings of heavy elements into the void. Think of it this way. If you analyse the chemical composition of someone's body, you could tell roughly what era they lived in. Someone from the medieval period would have different trace elements than someone from the industrial age. Methuselah's composition is the stellar equivalent of finding someone whose body chemistry suggests they're from the cosmic Middle Ages, so early that the universe was still learning how to make anything other than hydrogen and helium. This is what makes Methuselah so valuable to astronomers. It's not just old, it's chemically ancient, a relic from the era when the first generation of stars had just died, when galaxies were still assembling from smaller pieces, when the universe was beginning its long, patient work of building complexity from simplicity. And here's the beautiful part, that chemistry is permanent. Stars don't gather new material from space as they age. They're born with what they have and keep it. So Methuselah is a time capsule, carrying information about the conditions in the early universe, sealed away for 13 billion years, waiting for curious humans with spectroscopes to decode its message. We are reading a letter written in starlight, and the letter says, "I am from the beginning." Now, where exactly does Methuselah sit in its life story? Stars, like people, go through phases. There's the main sequence, the long, stable middle age where they spend most of their lives quietly fusing hydrogen in their cores. Then comes the subgiant phase, a sort of transitional period where the core hydrogen has run out and things start to get complicated. After that, if you're a star like Methuselah, you become a red giant, swollen, luminous, burning helium in your core and hydrogen in a shell around it. Eventually you shed your outer layers and leave behind a white dwarf, a dense ember that will cool for trillions of years. Methuselah is in that middle transition. It's a subgiant, past its prime, you might say, though that feels a bit unfair given it's been burning for 13 billion years. The hydrogen in its core is mostly exhausted, so the core is contracting under its own gravity, heating up. The outer layers are beginning to expand in response. It's not yet a red giant, not dramatically puffed up and luminous, but it's heading that way. Slowly, patiently, as stars do. This phase is crucial for age estimates. You see, where a star sits on what astronomers call the Hertzsprung-Russell diagram, a map of stellar brightness versus temperature, tells you how far along it is in its evolutionary journey. And if you know the star's mass and chemical composition, you can calculate how long it takes to reach each phase. It's like looking at someone's appearance and making an educated guess about their age. Except instead of grey hair and wrinkles, you're measuring luminosity and surface temperature. Methuselah's position on this diagram, right at the subgiant branch, is the stellar equivalent of being in your late 60s or early 70s. Not quite elderly, but definitely past middle age. For a star of its mass and composition, reaching this point takes about 13 billion years. Give or take a few 100 million, which in cosmic terms is a rounding error. The beautiful thing about stellar evolution is how slowly it unfolds for stars like this. Low-mass stars burn their fuel efficiently, sipping rather than gulping. Massive stars race through their lives in mere millions of years, exploding as supernovae before the universe has even noticed they exist. But stars like Methuselah, smaller, cooler, more patient, can burn for tens of billions of years. They're the tortoises of the cosmos, slow, steady, enduring. And this slowness is precisely why Methuselah can be so old. It was born with less mass than the Sun, which means it's been burning its hydrogen frugally, making each atom count. Even after 13 billion years, it still has fuel left. It's not done yet. It will continue burning for another 5 billion years or so, before it finally swells into a red giant, sheds its outer layers, and settles down as a white dwarf to cool for the rest of eternity. So when we look at Methuselah now, we're seeing it in a particular moment of a very long life. Not at the beginning, not at the end, but somewhere in the patient middle. Still burning, still here. Methuselah wasn't always famous. For most of its 13 billion year existence, it burned in complete anonymity, unobserved and unremarked upon. Even after humans evolved and started looking up at the night sky, cataloguing stars and giving them names, Methuselah remained just another faint point of light. It was first catalogued in the 19th century, probably by someone dutifully recording positions and brightnesses, filling in another blank space on the celestial map. Just a number. HD 140283 from the Henry Draper catalogue. No indication that this particular star was anything special. To the astronomers of that era, it was simply too faint to see without a telescope, too distant to show a measurable parallax with their instruments, and therefore too unremarkable to warrant much attention. Then came spectroscopy, the ability to split starlight into its component colours and read the chemical signatures hidden in those colours. By the mid-20th century, astronomers could analyse the light from stars like Methuselah and decode what they were made of. And that's when things got interesting. Someone, likely in the 1950s or 60s, during the golden age of stellar spectroscopy, pointed a telescope at HD 140283 and noticed its spectrum looked odd. Very few spectral lines from heavy elements, almost pure hydrogen and helium. This was the signature of extreme age. Stars born recently from gas enriched by countless previous stellar generations have rich spectra full of metal lines. But Methuselah's spectrum was sparse, primitive. It had clearly formed from ancient, unpolluted gas. By the 1970s and 80s, astronomers recognized Methuselah as one of the oldest known stars in the Milky Way. It became a valuable test case for stellar evolution models. If you wanted to understand how the first generations of stars formed and aged, you studied stars like this, chemically ancient, still surviving, close enough to observe in detail. But the real revolution came with better distance measurements. You see, to calculate a star's age, you need to know how far away it is. Distance tells you the star's true brightness, which combined with its temperature tells you where it sits on the evolutionary track, which tells you how old it is. Early estimates of Methuselah's distance were rough. Large error bars, significant uncertainty. And with that uncertainty came uncertainty in age. Then, in 2013, the Hubble Space Telescope measured Methuselah's parallax with unprecedented precision. Parallax is the apparent shift in a star's position as Earth orbits the Sun, the same effect you see when you hold your finger in front of your face and close one eye then the other. Nearby stars shift more, distant stars shift less. Measure that tiny angle precisely enough, and you can calculate exactly how far away the star is. Hubble's measurement tightened the distance estimate significantly, and when astronomers recalculated Methuselah's age with this better data, they got a number that made them pause. 14.5 billion years, older than the universe. That's when Methuselah became famous. That's when this quiet, ancient star, burning patiently for 13 billion years in relative obscurity, suddenly became the centre of a cosmic paradox. And then came Gaia. The European Space Agency's astrometry mission, launched in 2013, designed to measure the positions, distances and motions of over 1 billion stars with extraordinary precision. Gaia looked at Methuselah too, and what it found would eventually help resolve the paradox. But we're getting ahead of ourselves. So here we are with a star that appears impossibly old, but before we can understand why the numbers broke down, we need to understand how those numbers were calculated in the first place. How do you measure the age of something you can never touch, never sample, never visit? How do you read time from light alone? It's a bit like cosmic archaeology, really, except instead of digging through layers of soil to find artifacts, you're decoding information carried in photons that have travelled across interstellar space. Every star is essentially a time capsule, and the trick is learning how to read what's written on the outside without being able to open it up and look inside. Stars don't have tree rings. They don't have radioactive isotopes we can measure to determine how long they've been decaying. They're balls of plasma so hot that any conventional method of dating simply evaporates. Everything we know about a star's age comes from understanding how stars evolve, where they sit in that evolution, and what that position tells us about how much time has passed since they were born. Let's start with the foundation, stellar evolution theory. This is the roadmap that stars follow throughout their lives, and it's surprisingly predictable. A star's fate is largely determined by one thing: its mass. How much material it was born with dictates almost everything that follows: how hot it burns, how long it lives, how it will die. Massive stars, 10, 20, 50 times the mass of the sun, burn hot and fierce. They race through their fuel like teenagers with their first paycheck, converting hydrogen to helium at prodigious rates. Their lives are spectacular but brief, ending in supernova explosions after just a few million years. They're the mayflies of the cosmos, beautiful, brilliant, ephemeral. Stars like our Sun, with medium mass, burn more moderately. They can fuse hydrogen for about 10 billion years before exhausting their cores and swelling into red giants. They get a decent run at existence, long enough to see planets form, long enough for life to potentially evolve on those planets, long enough to seem almost eternal from a human perspective. But stars like Methuselah, smaller, less massive, more frugal with their fuel, these are the endurance athletes of the universe. At about 8/10 the Sun's mass, Methuselah burns slowly and efficiently. Stars like this can persist for tens of billions of years, potentially longer than the current age of the universe. They're so long-lived that not a single one has ever died of old age. Every low-mass star that's ever been born is still out there somewhere, still burning. This is crucial for understanding Methuselah's age. Its low mass means it's built for longevity. It's not surprising that it survived for 13 billion years. What's surprising is where it currently sits in its evolutionary journey. Which brings us to the Hertzsprung-Russell diagram. If stellar evolution is the roadmap, the HR diagram is the map itself. It's one of the most elegant tools in astronomy, a simple graph that reveals profound truths about how stars live and die. On one axis, you plot a star's temperature. Hotter stars toward the left, cooler stars toward the right. On the other axis, you plot luminosity, how much light the star actually emits. Brighter stars at the top, dimmer stars at the bottom. And when you plot enough stars on this diagram, patterns emerge. There's the main sequence, a diagonal band running from hot and bright in the upper left to cool and dim in the lower right. This is where stars spend most of their lives, steadily fusing hydrogen in their cores. Our Sun sits comfortably on the main sequence, about halfway through its 10 billion year hydrogen burning phase. Then there's the giant branch up in the upper right, cool but extremely luminous stars that have exhausted their core hydrogen and swollen to enormous sizes. These are stars in their old age, burning helium in their cores or hydrogen in shells around exhausted cores. And in between, there's the subgiant branch, the transitional region where stars like Methuselah live. They've finished burning hydrogen in their cores, but haven't yet become full red giants. They're in the cosmic equivalent of late middle age, heading toward retirement, but not quite there yet. Here's where it gets clever. If you know a star's mass and chemical composition, theoretical models can predict exactly how long it takes to reach each position on the HR diagram. It's like having a detailed map of aging, where you can look at someone and say, based on your appearance and the conditions you were born into, you're probably this many years old. Methuselah sits right at the turn-off point, the place where stars leave the main sequence and begin their journey toward becoming giants. For a star of its mass and composition, reaching this point takes approximately 13 billion years. The models are quite precise about this. They account for how efficiently the star fuses hydrogen, how energy is transported from core to surface, how the star's structure changes as fusion products accumulate in the core. But here's where things get delicate. To place a star on the HR diagram accurately, you need to know two things: its luminosity and its temperature. Temperature you can get from its spectrum. The colour of its light tells you how hot its surface is, but luminosity is trickier. Luminosity is how much light the star actually emits, its true brightness. But what we measure from Earth is apparent brightness, how bright the star appears to us. And the relationship between apparent brightness and luminosity depends entirely on distance. A dim star that's close can appear as bright as a luminous star that's far away. It's like trying to judge how bright two light bulbs are when one is across the room and the other is in the next building. This is why distance measurements are absolutely crucial for age estimates. Get the distance wrong and you get the luminosity wrong. Get the luminosity wrong and you place the star in the wrong spot on the HR diagram. Get that wrong and your age estimate is off by potentially billions of years. So how do we measure distance? For nearby stars like Methuselah, we use parallax, arguably the most elegant application of basic geometry in all of astronomy. As Earth orbits the Sun, our viewpoint shifts. We see nearby stars from slightly different angles at different times of year, just like you see your finger shift position when you look at it with one eye, then the other. The closer the star, the bigger the shift. The farther the star, the smaller the shift. Measure that tiny angular shift, that parallax, and you can calculate the distance with pure trigonometry. It's beautiful in its simplicity. No assumptions needed, no complex models required. Just geometry, the same kind that ancient Greeks used to measure the size of the Earth. The problem is that stellar parallaxes are tiny, astonishingly tiny. Even the nearest stars shift by less than 1 arcsecond, less than 1/3600th of a degree. Methuselah, at 190 light-years, has a parallax of about 17 milliseconds. That's roughly the angle subtended by a coin seen from 200 kilometers away. For centuries, measuring such tiny angles was at the very edge of what was possible. Early telescopes, limited by Earth's turbulent atmosphere and mechanical imperfections, could barely measure parallaxes at all. By the 20th century, ground-based instruments could get decent measurements for nearby stars, but with significant uncertainty, error bars of 10 or 20% weren't unusual. Then came space telescopes. Above the atmosphere, freed from the blurring and shimmering that plagues ground-based observations, parallax measurements became dramatically more precise. The Hipparcos satellite in the 1990s improved matters considerably. The Hubble Space Telescope, with its exquisite optics and stable pointing, refined things further. But the real revolution came with Gaia. Launched in 2013 by the European Space Agency, Gaia is doing something extraordinary, measuring the positions, distances and motions of over 1 billion stars with unprecedented precision. Its parallax measurements are accurate to a few dozen micro-arcseconds, millionths of a degree. For Methuselah, Gaia's measurements reduce the distance uncertainty to about 1%. Suddenly, instead of knowing the star was somewhere between 180 and 200 light-years away, we knew it was 190.1 light-years away, give or take 2 light-years. That's extraordinary precision, and precision in distance means precision in luminosity, which means precision in age. But distance is only part of the puzzle. To calculate a star's age accurately, you also need to understand its internal structure and evolution. And that depends heavily on its chemical composition, specifically its metallicity. We talked earlier about how Methuselah has very low metallicity, almost pure hydrogen and helium, with barely a trace of heavier elements. This matters enormously for how the star evolves. Heavy elements, even in small amounts, affect how easily energy escapes from the star's interior. They increase opacity. Basically, they make it harder for photons to work their way out from the core to the surface. High metallicity stars, like the Sun, are relatively opaque. Photons scatter off metal atoms, bouncing around inside the star for thousands of years before finally escaping. This trapped energy makes the star hotter and more luminous than it would be otherwise. Low metallicity stars like Methuselah are more transparent. With fewer metal atoms to scatter off, photons escape more easily. The star runs cooler and dimmer for its mass, and crucially, it evolves differently. Lower opacity means different internal temperature gradients, different convection patterns, different rates of fuel consumption. Early stellar models often used solar metallicity opacity tables because that's what was available and well understood. But applying solar metallicity assumptions to a star with 1/250th the Sun's metal content is like trying to predict how a vegetarian will react to a diet by studying carnivores. The models have to be adjusted for the star's actual composition. When astronomers did this, when they built models specifically for low metallicity stars, the predicted evolutionary timescales changed. Not dramatically, but enough to matter. A few 100 million years here, a few 100 million there. These corrections would become important later, when trying to reconcile Methuselah's age with the universe's age. Then there's helium. Helium is frustratingly difficult to measure in cool stars like Methuselah because it doesn't produce strong spectral lines at the star's surface temperature. Hydrogen you can see clearly. Heavy metals you can measure precisely. But helium hides in the spectrum, neither fully visible nor completely absent. Yet helium abundance matters enormously for stellar evolution. More helium means higher mean molecular weight in the star's interior, which affects core pressure and temperature, which affects fusion rates, which affects how long the star can burn. A difference of just 2% in helium abundance can shift the age estimate by several 100 million years. So astronomers have to infer helium abundance indirectly, using models of Big Bang nucleosynthesis, the process that created the primordial helium in the first few minutes after the universe began, combined with estimates of how much additional helium the star might have produced through its own fusion. It's educated guesswork, constrained by physics, but guesswork nonetheless. And then there are the nuclear reaction rates themselves. The age of a star depends on how fast it burns its fuel, which depends on the probability that hydrogen nuclei will fuse when they collide. These probabilities, These cross-sections in physics terminology have been measured in laboratories and calculated from quantum mechanics, but they're not perfectly known. There are uncertainties, especially for some of the rarer reactions. A 5% uncertainty in reaction rates translates to a few 100 million years in age. Not huge, but not negligible either when you're trying to determine if a star is older than the universe. More recently, astronomers have moved from simple one-dimensional stellar models to sophisticated three-dimensional simulations. Real stars aren't perfectly spherical and smooth. They have convection cells, turbulence, magnetic fields. Their atmospheres are dynamic and complex. Three-dimensional models capture this complexity in ways that older models couldn't. When you run these 3D models for stars like Methuselah, the predicted surface properties change slightly. Temperature, pressure, the way spectral lines form. Everything shifts a bit. And those shifts mean the star's position on the HR diagram shifts too, which means the age estimate shifts. Each of these corrections is small. Distance, opacity, helium, nuclear rates, atmospheric models. Individually, they might shift the age by a few 100 million years, but they're not independent. They interact, they compound, and when you add them all up, carefully and precisely, the age estimate can change by more than 1 billion years. This is the challenge of stellar dating. You're trying to extract a single number, age, from a cascade of measurements and models, each with its own uncertainty, each affecting the others. You're solving a puzzle where every piece has fuzzy edges, and you're never quite sure if you have all the pieces in the right places. But astronomers are patient. They measure carefully, they refine their models, they build better instruments, and slowly, piece by piece, the picture comes into focus. For Methuselah, that picture initially showed a star that was 14.5 billion years old, impossibly old, older than the Big Bang. Something somewhere had to be wrong. And finding out where the errors hide, that's where the story gets really interesting. Now we arrive at the heart of the paradox. All those careful measurements, all that theoretical modelling, all that patient accumulation of data, and the number that emerged was impossible. Methuselah's age, according to early 21st century estimates, 14.5 billion years, give or take 800 million years. The age of the universe, according to measurements of the cosmic microwave background, 13.8 billion years, give or take about 20 million years. You don't need a PhD in astrophysics to see the problem. Even accounting for the uncertainties, those give-or-take margins that represent the honest admission that measurements are never perfect, the numbers barely touch. At the lower end of Methuselah's age estimate, you get 13.7 billion years. At the upper end of the universe's age, you get 13.82 billion years. The margins kiss, briefly, in a narrow range where both could theoretically coexist. But that's being generous. That's squinting at the error bars and saying, well, technically, maybe, if everything breaks in the right direction. In reality, the most likely age for Methuselah sat squarely outside the most likely age for the universe. The star appeared to be about 700 million years older than the Big Bang, which is, to put it mildly, awkward. This wasn't some fringe calculation by a lone researcher with questionable methodology. These were mainstream results, published in respected journals, derived using standard techniques by competent astronomers who check their work multiple times before going public. The distance measurements came from Hubble. The stellar models were state-of-the-art. The cosmological age came from the Wilkinson microwave anisotropy probe, and later the Planck satellite, some of the most precise instruments humanity has ever built. And yet the numbers didn't line up. Something, somewhere, had to be wrong. The question was, what? Let's pause for a moment and appreciate the magnitude of this problem. Methuselah would have to have formed 700 million years before the universe existed. Before time, before space, before anything. It's not just improbable, it's logically incoherent in a way that makes your brain itch when you try to hold the concept there for too long. Imagine telling someone that your grandmother was born 3 years before her mother. Now imagine that instead of family records, you're dealing with the fundamental timeline of existence itself, calibrated by multiple independent methods that all agree with each other to within a fraction of a percent. That's the situation astronomers found themselves in. The cosmic equivalent of finding your birth certificate dated before your parents met. The astrophysics community reacted the way you'd expect, with fascination, skepticism, and a certain grim determination to figure out where the error was lurking. Papers were published examining every assumption in the age calculation. Conferences featured heated but collegial debates about stellar models, distance measurements, and cosmological parameters. Graduate students wrote dissertations on Methuselah. The star became famous, or infamous depending on your perspective, as the Methuselah problem. The stakes were higher than just one star's age. If stellar ages were systematically wrong, that meant globular clusters, ancient collections of stars used to calibrate cosmic history, were also misdated. If the universe's age was wrong, that meant our understanding of cosmic expansion, dark energy, and the fundamental parameters of cosmology needed revision. Neither option was comfortable. Both had implications that rippled through decades of accumulated knowledge. Some astronomers suspected the stellar models. Maybe our understanding of how low metallicity stars evolve was incomplete. Maybe there were physical processes we hadn't accounted for. Exotic mixing mechanisms, unusual opacity effects, something subtle that threw off the age estimates by 1 billion years. Stars are complex objects with interiors we can never directly observe after all. We infer everything from surface properties and theoretical models. Perhaps the models were missing something important. Others looked at the distance measurements. Even Hubble's parallax, impressive as it was, had uncertainties. Maybe Methuselah was closer than thought, which would make it less luminous, which would make it younger. Or maybe there were systematic errors in the parallax reduction process, ways that the raw data could be misinterpreted, biases that crept in unnoticed during the analysis. Parallax measurements are devilishly difficult, requiring you to detect angular shifts smaller than a coin seen from 200 kilometers away. There's a lot of room for subtle errors. A few even questioned the universe's age, though this was harder to argue. The cosmic microwave background measurements were extraordinarily precise and internally consistent. Multiple independent analyses of the same data, using different statistical techniques and different assumptions, all converged on 13.8 billion years. The uncertainties were tiny, just 20 million years, barely a rounding error in cosmic terms. To make room for a 14.5 billion-year-old star, you'd need to be wrong by 700 million years, which is 35 times larger than the stated uncertainty. That's substantial. That's not, we might have made a small mistake territory. That's, we fundamentally misunderstand something territory. But here's something important to understand. The universe's age isn't derived from a single measurement. It comes from fitting multiple observations to a theoretical model, the lambda CDM model, our current best description of cosmic evolution. This model has parameters, the Hubble constant, how fast the universe is expanding, the density of matter, the density of dark energy, the geometry of space, and others. Adjust these parameters, and the calculated age changes. The cosmic microwave background gives us an exquisitely detailed baby picture of the universe at 380,000 years old. The patterns of hot and cold spots in that ancient light encode information about the universe's composition and geometry. Feed that information into the lambda CDM model, turn the mathematical crank, and out comes an age, 13.8 billion years. But, and this is crucial, that age depends on the model being correct. If lambda CDM is missing something, if there's physics we don't understand affecting cosmic expansion, then the derived age could be wrong even if the measurements are perfect. It's a bit like using a map to estimate travel time. If your map is accurate and you know the speed limit, you'll get the right answer. But if there's construction you don't know about, or if the speed limit has changed, or if your car runs slower than you thought, your estimate will be off, even though you did everything right with the information you had. So the Methuselah paradox raised uncomfortable questions. Not just, where's the measurement error, but is our understanding of cosmology as solid as we think it is? Could there be unknown physics, new particles, evolving dark energy, modifications to gravity that would change the universe's age? It seemed unlikely, but the paradox forced people to at least consider the possibility. Let's step back and think about timelines for a moment, because this is where the impossibility becomes truly visceral. The Big Bang happens, space-time begins, not just space appearing in time, but time itself coming into existence, which is a thought that makes even physicists pause and shake their heads slightly. The universe is unimaginably hot and dense, a roiling sea of energy and particles where matter and antimatter annihilate each other, where forces we now think of as distinct are unified, where nothing remotely like a star or a galaxy or even an atom can exist. For the first 380,000 years, it's completely opaque. Photons can't travel freely because they constantly scatter off the plasma of charged particles. Every photon that tries to go anywhere immediately collides with an electron or a proton and bounces in a different direction. Light exists, but it can't propagate. The universe is luminous but unseeable, like being inside a glowing fog so thick you can't see your hand in front of your face. Then the universe cools enough for atoms to form. Electrons and protons combine to make neutral hydrogen. Suddenly photons have nowhere to scatter. They can finally travel freely through space. That's when the cosmic microwave background is released, carrying its encoded message about the infant cosmos. That ancient light stretched and cooled by 13.8 billion years of cosmic expansion is what satellites like WMAP and Planck have measured with such extraordinary precision. But stars can't form yet. The universe is still too smooth, too uniform. Gravity needs time to pull matter together into clumps, to amplify the tiny density fluctuations that existed in the early universe. Dark matter, which doesn't interact with light or ordinary matter except through gravity, begins to collect into halos, pulled together by its own gravitational attraction. These halos grow, merge, become the gravitational wells where ordinary matter can gather. Eventually, hundreds of millions of years after the Big Bang, the first gas clouds become dense enough to collapse under their own gravity. They heat up as they contract, and finally, when the core temperature reaches millions of degrees, nuclear fusion ignites. The first stars are born. These population 3 stars are unlike anything we see today, made of pure primordial gas, no carbon, no oxygen, no iron, nothing but hydrogen and helium. They likely form with enormous masses, 50, 100, perhaps even several hundred times the mass of our Sun. They burn with ferocious intensity, blazing hot and blue, pouring ultraviolet radiation into the cosmos and beginning the process of reionizing the neutral hydrogen that fills space. But they don't last. Massive stars burn through their fuel in just a few million years. They fuse hydrogen to helium, helium to carbon and oxygen, continue up the periodic table until their cores are iron, and then, having no more fusion energy to generate, they collapse catastrophically and explode as supernovae. Perhaps the most energetic events in the universe aside from the Big Bang itself. These explosions scatter the first heavy elements into space. Not much. A population 3 supernova might produce only a few solar masses of carbon, oxygen, silicon, iron. But it's enough. Enough to change the chemistry of the surrounding gas from purely primordial to slightly enriched. Enough to allow the next generation of stars to form with different properties. Smaller, longer-lived, more varied. Methuselah is second generation population 2. It formed from gas enriched by those first supernovae, which means it can't have formed immediately after the Big Bang. There has to be a gap, time for the universe to cool and for dark matter to clump. Time for population 3 stars to form, perhaps 100 to 300 million years after the Big Bang. Time for those stars to live, a few million years. Time for their ejector to cool and mix with the surrounding gas. Another few million years at least. Time for that enriched gas to collapse into new stars. Realistically, you need at least 500 million years, probably more, between the Big Bang and Methuselah's formation. Some models suggest it could be as much as 800 million years before you get conditions suitable for forming a star with Methuselah's low but non-zero metallicity. Which means if the universe is 13.8 billion years old, Methuselah should be at most 13.3 billion years old, more likely around 13 billion years old or even a bit younger. But the measurement said 14.5 billion years. The timeline was squeezed impossibly tight. Even if you pushed everything to its extreme, population 3 stars forming as early as possible, living as briefly as possible, Methuselah forming immediately afterward with no gap, the universe being as old as the upper error bars allowed, you still couldn't make it work. Not comfortably, not without straining credibility. The numbers simply refused to align. This is what made the paradox so compelling. It wasn't just a discrepancy, it was a discrepancy that revealed the intricate web of assumptions underlying both stellar evolution theory and cosmology. Pull on one thread, and you had to examine all the others to see where they might be fraying. Question one measurement, and you had to question them all. The whole edifice of cosmic chronology suddenly felt a bit less stable. The media predictably had a field day with it. Headlines proclaimed "star older than the universe," with varying degrees of accuracy and sensationalism. Some articles implied that the Big Bang theory was in crisis, which was overstating things considerably. Others treated it as a curiosity, a quirky anomaly that scientists would sort out eventually, probably over tea and scones. Public reaction was mixed. Some people found it fascinating, a genuine cosmic mystery, the kind of thing that makes you lie awake at night, wondering how it could possibly be resolved. It had that delicious quality of being simultaneously absurd and scientifically rigorous. Others saw it as evidence that scientists don't really know what they're talking about, that all these confident pronouncements about the age of the universe are just guesswork dressed up in fancy mathematics. But here's the thing, this is how science is supposed to work. You make measurements, you build models, you compare the two, and when they don't agree, you don't panic, you investigate, you check your instruments, you refine your models. You look for systematic errors, hidden assumptions, overlooked effects. You sit with the tension between what you measured and what you expected, and you use that tension as a guide to deeper understanding. The Methuselah paradox wasn't a failure of science. It was science doing exactly what it's designed to do, confronting inconvenient data honestly, refusing to sweep anomalies under the rug, and trusting that careful investigation will eventually reveal where the truth lies. The paradox was uncomfortable, yes. But discomfort is often the price of progress. And the truth, as it turned out, was subtle. The paradox wasn't the result of one big error, but rather a cascade of small uncertainties that compounded into an impossible result. The distance was slightly off. The opacity models were slightly off. The helium abundance assumptions were slightly off. The nuclear reaction rates had small uncertainties. The atmospheric models needed refinement. None of these individually was a disaster, but together, in the specific combination that applied to Methuselah, they conspired to make the star appear older than it really was. It's like a series of small navigation errors on a long journey, each one nudging you slightly off course, and by the time you notice, you're miles from where you thought you were. Finding those errors, quantifying them, correcting them, that would take time. Better instruments, more sophisticated models, patience. But even before all the corrections were applied, before Gaia's exquisite measurements refined the distance, before 3D stellar models adjusted the age downward, astronomers understood something important. The paradox was narrow, the margins were tight. They weren't off by 10 billion years or even 5 billion years. They were off by less than 1 billion, possibly much less. Which meant the solution was probably hiding in the details, in the error bars, in the assumptions that seemed too small to matter, but actually mattered quite a lot when you added them all together. The paradox wasn't pointing to revolutionary new physics or a fundamental misunderstanding of the cosmos. It was pointing to the accumulated uncertainty of many small measurements. The universe, it seemed, hadn't broken its own timeline. It had simply revealed how difficult it is to measure that timeline with perfect accuracy, how every number in cosmology and astrophysics is connected to every other number, how precision in one area doesn't help if you have uncertainty in another, how even the most careful measurements carry whispers of doubt. Methuselah stood at the centre of this web of uncertainties, burning patiently, indifferent to the confusion it had caused. The star hadn't changed. It had been 13 billion years old all along, more or less. We were the ones who had measured it incorrectly, who had built models that needed refining, who had assembled our best understanding of cosmic history and found it slightly, but significantly, askew. The paradox wasn't in the star. It was in us, in our tools, our models, our measurements, in the inevitable gap between what the universe is and what we can discern about it from hundreds of light years away, with instruments that, however sophisticated, are still fundamentally limited by the laws of physics. So, we have an impossible star, or rather, we have a star that appears impossible because our measurements and models have conspired to produce an age that doesn't fit within cosmic history. Now comes the careful, patient work of finding where the errors hide. This is detective work, really. Forensic astronomy. You have a result that you know is wrong, or at least strongly suspect is wrong, and you need to trace backward through every calculation, every assumption, every measurement, looking for the places where small uncertainties accumulated into a large problem. The first thing to understand is that all measurements have uncertainty. This isn't a flaw or a failure, it's simply the nature of observation. When you measure something, you're always working with finite precision. Your ruler has minimum markings. Your scale has a smallest increment. Your telescope has limits to how precisely it can determine a star's position or brightness. and every one of these limitations propagates forward through your calculations. In astronomy, we deal with objects we can never touch, never sample, never visit. We're measuring things across distances so vast that light takes hundreds or thousands of years to reach us. We're inferring properties, temperature, composition, luminosity, from the faint whisper of photons that happen to arrive at our detectors. It's a bit like trying to reconstruct what someone looks like, based on a rumour you heard from someone who once saw their shadow. You can do it, with enough cleverness and careful reasoning, but the result will always carry uncertainty. For Methuselah, that uncertainty came from multiple sources, each contributing its own small doubt to the final age estimate. And when you stack uncertainties together, they don't just add, they multiply, compound, interact in ways that can produce surprisingly large effects. This is one of the subtle challenges of precision measurement. Errors don't behave politely. They propagate through calculations in complex ways, sometimes cancelling each other out, sometimes reinforcing each other, always making the final answer fuzzier than you'd like. Let's start with distance, because distance is foundational to almost everything else. To know a star's true brightness, its luminosity, you need to know how far away it is. And distance for stars like Methuselah comes from parallax. We've already talked about parallax, the apparent shift in a star's position as Earth orbits the Sun, measured in tiny angles that require extraordinary precision to detect. Early measurements of Methuselah's parallax, done from ground-based observatories through Earth's turbulent atmosphere, had uncertainties of perhaps 10 or 20%. That's not bad for ground-based work. It's actually quite impressive given the difficulties, but it's not great either when you're trying to pin down an age to within a few 100 million years. When the Hubble Space Telescope measured Methuselah in 2013, the uncertainty dropped dramatically. Hubble, orbiting above the atmosphere with its exquisite optics and stable pointing, could measure parallax to perhaps 2 or 3% precision. Suddenly, the distance was known much better, 190 light-years, give or take 5 or 6. But here's the subtle part. A 5% uncertainty in distance becomes a 10% uncertainty in luminosity. That's because luminosity depends on distance squared, the inverse square law of light. Move a star twice as far away, and it appears 4 times dimmer. So if you're uncertain about distance by 5%, you're uncertain about luminosity by roughly 10%. The error gets amplified through the mathematics, and that 10% uncertainty in luminosity translates to uncertainty in where the star sits on the Hertzsprung-Russell diagram, which translates to uncertainty in age. A star that's 10% more luminous than you thought is further along in its evolution, which means it's older. A star that's 10% less luminous is younger. The effect compounds through each step of the inference chain. For Methuselah, early distance uncertainties alone could easily shift the age estimate by 500 million years or more. Get the distance wrong in one direction, and the star appears younger. Wrong in the other direction, older. And when your measured age is already uncomfortably close to the universe's age, a 500 million year swing becomes very significant indeed. Then came Gaia, the European Space Agency's astrometry mission, purpose-built to measure stellar positions and distances with unprecedented precision. Gaia doesn't just observe a few stars carefully, it observes over 1 billion stars, repeatedly, building up measurements over years to achieve accuracies measured in micro-arcseconds, millionths of a degree. The spacecraft spins slowly, scanning the entire sky, measuring each star dozens of times, averaging out errors, refining positions with each observation. For Methuselah, Gaia refined the distance to about 1% uncertainty. 190.1 light-years, give or take 2. That's extraordinary. That's measuring the width of a human hair from across a football field. And with that precision, one major source of uncertainty in the age estimate essentially vanished. The distance refinement alone dropped Methuselah's age by roughly 500 million years. Not because the star changed, but because we finally measured accurately where it actually was. It was slightly closer than earlier estimates suggested, which meant it was slightly less luminous, which meant it was slightly younger. 500 million years of apparent age, erased by better measurement. That's a significant chunk of the paradox right there. But distance was only the first correction. The next place errors hide is in stellar opacity, how easily light escapes from a star's interior. Stars are not simple objects. They're layered spheres of plasma where energy generated in the core has to work its way out to the surface before it can escape as light. That journey can take thousands of years because photons keep scattering off particles, electrons, atoms, ions, bouncing around like pinballs until they finally reach the surface and stream off into space. The opacity of stellar material determines how long this journey takes, which affects the star's internal temperature structure, which affects how efficiently it burns fuel, which affects how it evolves over time. High opacity means energy gets trapped, the star runs hotter internally, burns faster. Low opacity means energy escapes more easily, the star runs cooler, burns more slowly. Metallicity affects opacity. Heavy elements, remember in astronomy anything heavier than helium, are particularly effective at scattering photons. They have more electrons, more complex atomic structures, more ways to interact with light. So high metallicity stars like the Sun have a higher opacity than low metallicity stars like Methuselah. Early stellar models often used opacity tables calculated for solar metallicity, simply because that's what was available and well understood. But applying solar opacity to a star with 1/250th the Sun's metal content is a bit like assuming everyone has the same metabolism, regardless of diet. It's approximately right in some ways, but the details matter. When astronomers developed opacity tables specifically for low metallicity stars, accounting for the fact that there are far fewer metal atoms to scatter photons, the models changed. Stars like Methuselah turned out to be slightly more transparent than previously thought, which meant they evolved slightly differently. The corrected models predicted ages about 200 to 300 million years younger. Not huge individually, but starting to add up. Then there's helium. Helium is the universe's second most abundant element, making up about 24% of the cosmos by mass. It's created in two ways, during the Big Bang's first few minutes, and later inside stars through hydrogen fusion. Every star that burns hydrogen produces helium, so over cosmic time the universe's helium abundance slowly increases. For age calculations, you need to know how much helium a star was born with. More helium means higher mean molecular weight in the star's interior, which means different internal pressures and temperatures, which means different fusion rates and evolutionary timescales. The problem is that helium is nearly invisible in stars like Methuselah. It doesn't produce strong spectral lines at the star's surface temperature, so you can't measure it directly the way you can measure iron or magnesium or calcium. You have to infer it from other information, models of Big Bang nuclear synthesis, assumptions about how much the first generation of stars enrich the gas, estimates of mixing and diffusion within the star itself. For very old low metallicity stars, the assumption is that they formed from gas that was close to primordial composition, the Big Bang's original helium fraction of about 24%, with only minor enrichment from the first generation of stars, but close to leaves room for interpretation. Is it 24%, 25%, 26%? A 2% difference in helium abundance can shift the age estimate by 400 to 500 million years. That's substantial. And because you can't measure helium directly, there's unavoidable uncertainty in this number. Early models sometimes assumed slightly higher helium abundances than were probably correct for such an ancient star. When astronomers revised these assumptions downward, using more refined models of Big Bang nucleosynthesis and early galactic chemical evolution, Methuselah got younger again. Another few 100 million years erased from the age estimate. Still not done. There are also uncertainties in nuclear reaction rates, the probabilities that govern how fast hydrogen fuses into helium inside the star's core. These rates have been measured in laboratories, where physicists slam protons together at high energies and count how often they fuse. They've also been calculated from first principles using quantum mechanics. The measurements and calculations generally agree quite well, but they're not perfect. There are uncertainties, especially for some of the more complex reaction chains. A 5% uncertainty in the primary fusion rate, the proton-proton chain that powers stars like Methuselah, translates to roughly a 3% uncertainty in the star's lifetime, which is about 300 or 400 million years for a 13-billion-year-old star. These uncertainties have been gradually refined over decades as experimental techniques improve and theoretical calculations become more sophisticated. Each refinement nudges the age estimate slightly, usually by small amounts, but occasionally by enough to matter. Then we get to atmospheric models. The atmosphere of a star, the outermost layers where light finally escapes into space, is where all our observations come from. The star's spectrum, its colour, its apparent brightness, all of these are determined by what's happening in the atmosphere. So if your model of the atmosphere is wrong, everything else gets skewed. For a long time, stellar atmosphere models were one-dimensional. They assumed spherical symmetry with properties varying only with depth, hotter and denser deeper in, cooler and thinner near the surface. Convenient for calculation, but not entirely realistic. Real stars aren't smooth spheres of gas sitting in perfect equilibrium. Real stellar atmospheres are three-dimensional. They have convection cells, rising columns of hot plasma and sinking columns of cool plasma, like water boiling in a pot. They have turbulence, temperature fluctuations, complex flows. They have granulation patterns on their surfaces, like the bubbling you can see on the sun if you look closely enough. All of this affects how light escapes, how spectral lines form, what we see when we observe the star. Modern three-dimensional atmosphere models, computed on powerful supercomputers that can simulate the complex fluid dynamics of stellar surfaces, capture this complexity. And when you apply these 3D models to stars like Methuselah, you get slightly different surface temperatures, slightly different emergent spectra, slightly different inferred luminosities. The effect is usually small, perhaps 100 or 200 million years in age, but it's systematic. If you use 1D models for all your stars, you'll get ages that are systematically biased in one direction. Switch to 3D models, and all your ages shift slightly. For Methuselah, the 3D corrections made the star appear slightly cooler and less luminous than 1D models predicted, which made it younger. Add it all up. Distance refinement from Gaia, improved opacity tables for low metallicity, revised helium abundance assumptions, better nuclear reaction rates, three-dimensional atmospheric models. Each correction is individually modest, a few 100 million years here, a few 100 million there. But together they accumulate, they compound. the age estimate dropped from 14.5 billion years to roughly 13 billion years. Some estimates go as low as 12.8 billion. The central value and the uncertainty range both shifted downward, bringing Methuselah comfortably within the universe's timeline. The paradox softened. The impossible star became possible again. But there's one more wrinkle in this story, one more source of uncertainty that affects not just Methuselah, but our understanding of cosmic history itself, the Hubble constant. The Hubble constant measures how fast the universe is expanding, specifically how quickly galaxies are receding from each other as space itself stretches. It's one of the most fundamental numbers in cosmology, and it directly determines how old the universe is. Faster expansion means the universe reached its current size more quickly, which means it's younger. Slower expansion means it took longer to get here, which means it's older. For decades, the Hubble constant was poorly known, uncertain by perhaps 20 or 30%. But modern measurements have dramatically improved precision. The problem is, they don't agree with each other. And this disagreement creates an interesting ambiguity in how we interpret Methuselah's age. Measurements based on the cosmic microwave background, observations of the universe when it was 380,000 years old, give a Hubble constant of about 67 kilometers per second per megaparsec. Plug that into the equations of cosmic expansion, and you get a universe age of 13.8 billion years. But measurements based on local observations using supernovae and other standard candles to map cosmic expansion in the relatively nearby universe give a Hubble constant of about 73 kilometers per second per megaparsec. That implies a universe age of about 13.0 billion years. The discrepancy is about 9%, and it's persistent. Both measurement methods are sophisticated and careful, with small quoted uncertainties. Multiple independent teams using different analysis techniques get similar results within each method. They shouldn't disagree this much, but they do. It's one of the biggest unsolved problems in cosmology right now, known as the Hubble tension. Here's the interesting part. If the local measurements are correct and the universe is only 13 billion years old, then Methuselah at 13 billion years fits perfectly. There's no paradox at all, or at most a very mild tension. The star formed within a few 100 million years after the Big Bang, which is early but entirely plausible, given what we know about early star formation. If the CMB measurements are correct and the universe is 13.8 billion years old, then Methuselah at 13 billion years is old, but comfortable. It formed about 800 million years after the Big Bang, giving plenty of time for population 3 stars to form and die first, for the gas to be enriched with metals, for the second generation to begin. Either way, once the stellar age corrections are applied, the paradox dissolves. Methuselah is no longer older than the universe under any reasonable interpretation of the data. The star fits within cosmic history. The timeline makes sense again. But the journey to this resolution reveals something profound about how science works at the frontier of knowledge. The paradox wasn't the result of one dramatic error or one fundamental misunderstanding. It was the result of many small uncertainties compounding in unfortunate ways. Distance, a bit too far. Opacity, not quite right for low metallicity. Helium, assumed slightly too high. Reaction rates, small uncertainties. Atmospheric models, one-dimensional approximation not quite accurate. Each individually plausible, each contributing a few 100 million years of error, and all of them happening to push the age estimate in the same direction, upward. It's like walking across a field while gradually veering slightly to the left with each step. No single step takes you dramatically off course, but after 1,000 steps, you're far from where you intended to be. The cumulative effect of small biases can produce large deviations. This is the challenge of precision astronomy. You're trying to extract absolute truth from measurements that are always uncertain and models that are always approximations. You're building a tower of inferences, each resting on the ones below, and hoping that the accumulated uncertainty doesn't topple the whole thing. Sometimes it does topple, or at least lean alarmingly, and when that happens, you don't despair. You carefully examine each level of the tower, testing each assumption, refining each measurement, improving each model. Slowly, patiently, you make the tower stable again. The Methuselah paradox is now resolved, or at least softened to the point where it no longer threatens our understanding of cosmic history. The star is ancient, genuinely ancient, one of the oldest objects we know, but not impossibly so. It fits within the universe's timeline, formed early, but not absurdly early, and continues burning patiently, as it has for 13 billion years. The universe accommodated it all along. We were the ones who needed to refine our measurements to see clearly. So the paradox has resolved itself, or at least narrowed to the point where it no longer threatens the foundations of cosmology. Methuselah is ancient, but not impossible. It fits within the universe's timeline, if just barely. But now that we've established when the star formed, we can ask a more interesting question. What does its existence tell us about those early days of cosmic history? Methuselah is more than just a curiosity, more than just a measurement challenge that kept astronomers busy for a few years. It's a messenger from the deep past, a time capsule, a fossil that remembers when the universe was young and still figuring out how to make things more complex than hydrogen and helium. Think about what it means for a star to be 13 billion years old. That's 94% of the universe's entire history. When Methuselah formed, the universe was less than 1 billion years old, a cosmic infant by any measure. Galaxies were still assembling from smaller pieces. The first generation of stars had only recently died. The heavy elements we take for granted, carbon, oxygen, silicon, iron, barely existed. This star has witnessed almost everything. It was burning when the first galaxies collided and merged. It watched as the cosmic web of large-scale structure slowly emerged from tiny fluctuations in the primordial density field. It saw the Milky Way assemble from dozens of smaller galaxies, cannibalizing them one by one, growing from a modest collection of stars into the magnificent spiral we inhabit today. And through all of that, through 13 billion years of cosmic evolution, through galaxy mergers and stellar births and supernovae and every dramatic event you can imagine, Methuselah just kept burning, quietly, patiently, converting hydrogen to helium, 4 protons at a time, generating a steady trickle of energy that sustained it across geological ages that make Earth's history seem like a brief afternoon. Let's talk about what came before Methuselah, because that context is crucial for understanding what the star represents. The very first stars, population 3 as astronomers call them, were nothing like what we see today. They formed from gas that was purely primordial, hydrogen and helium created in the Big Bang's first few minutes, with nothing else mixed in. No carbon to help the gas cool and fragment into smaller clouds. No oxygen, no silicon, no iron. Just the 2 simplest elements. And that chemical simplicity had profound consequences for how stars could form. Without heavier elements to radiate energy away efficiently, gas clouds in the early universe couldn't cool below a certain temperature, and if they couldn't cool, they couldn't collapse into small, dense clumps. They had to be massive, very massive, to generate enough gravitational pressure to overcome the thermal pressure trying to keep them expanded. So the first stars were probably enormous, 50, 100, perhaps several hundred times the mass of our Sun. They would have burned with incredible ferocity, pouring ultraviolet radiation into the cosmos, heating the surrounding gas, ionizing hydrogen atoms across vast distances. They were beacons in the cosmic dark ages, lighting up a universe that had been black and cold for hundreds of millions of years. But they didn't last. Massive stars burn through their fuel at prodigious rates. A star with 100 solar masses might exhaust its core hydrogen in just a few million years, a cosmic eye blink. And when they died spectacularly, exploding as supernovae that released more energy in seconds than the Sun will emit in its entire 10 billion year lifetime. Those explosions were crucial. They took the heavy elements that had been forged inside the star's core, carbon, oxygen, neon, magnesium, silicon, iron, and scattered them into space. They enriched the primordial gas, adding a tiny but crucial dash of metallicity to the universe's chemistry, and that enrichment changed everything. Gas, with even a small amount of heavy elements, cools more efficiently. Carbon and oxygen atoms can absorb and re-emit energy at specific wavelengths, carrying heat away through radiation. This means enriched gas can fragment into smaller clouds, which means smaller stars can form. The second generation of stars, population 2, Methuselah's generation, could have a much wider range of masses. Not just giants, but medium-sized stars and small ones, stars that could burn for billions of years instead of millions. Methuselah's chemistry tells us it formed from gas that had been enriched by this first generation, but only barely. Its metallicity is about 1/250th of the Sun's. That's almost nothing, but it's enough. Enough to mark it as second generation, enough to tell us that at least one population 3 star had lived and died before Methuselah was born, and probably several. The timeline must have been tight. Population 3 stars probably started forming around 100 to 300 million years after the Big Bang. They burned for a few million years. Their supernovae enriched the gas. That enriched gas cooled, collected in dark matter halos, and collapsed to form the next generation. All of this had to happen fast enough that Methuselah could form around 500 to 800 million years after the Big Bang. That's an extraordinarily rapid transformation. In the cosmic blink of an eye, the universe went from total darkness to stars, from stars to supernovae, from supernovae to the chemical seeds of everything that would follow. The early universe was not patient. It did not wait. It rushed headlong into complexity with an almost unseemly haste. Methuselah's existence confirms this rapid timeline. If the early universe had been slower to form stars, if population 3 had taken longer to emerge, if the enrichment process had been inefficient, then stars like Methuselah couldn't have formed as early as they did. The star is proof that the cosmic machinery was working quickly and effectively in those first few 100 million years. And it's not just Methuselah. The star is part of a larger story being revealed by modern observations. The James Webb Space Telescope, peering deeper into the early universe than we've ever looked before, has found surprisingly mature galaxies existing less than 1 billion years after the Big Bang. Galaxies that are more massive, more structured, more chemically enriched than many theorists expected. The early universe appears to have been very good at making stars and very efficient at assembling those stars into galaxies. This efficiency has implications for our understanding of how structure formed in the cosmos. Dark matter halos must have assembled quickly. Gas must have fallen into those halos and cooled rapidly. Star formation must have begun almost as soon as it was physically possible. The universe wasted no time in getting busy with the work of creating complexity. There's something else Methuselah tells us. It probably didn't form where it is now. The star's orbit is all wrong for a disk star. It's moving too fast in the wrong direction on an eccentric path that takes it swooping through the Milky Way's halo rather than circling sedately in the galactic plane like the Sun does. This is the signature of a halo star, an ancient object that was either born in the Milky Way's diffuse outer regions or, more likely, was born in a completely different galaxy that was later absorbed. The Milky Way is a cannibal. It has consumed dozens of smaller galaxies over its history, tearing them apart with its gravity, scattering their stars across the halo, adding their mass to its own. We can still see the remnants of this cosmic violence. Stellar streams, long, coherent trails of stars that trace the orbits of disrupted dwarf galaxies. The Sagittarius dwarf galaxy, currently being shredded as we speak, stretched out in a long arc around the Milky Way like taffy being pulled apart. Methuselah could be a survivor of one of these ancient mergers. Perhaps it formed in a small dwarf galaxy that was consumed billions of years ago, its former home completely destroyed, its companion stars scattered to the cosmic winds. Now it wanders through the Milky Way like an exile, a refugee from a nation that no longer exists, carrying within its spectrum the only remaining evidence that its birth galaxy ever was. This makes Methuselah even more remarkable. Not only is it ancient, not only does it carry information about the early universe's chemistry, but it may have witnessed the violent assembly of our galaxy. It might have been there when its home galaxy collided with the proto-Milky Way, when the gravitational interaction triggered bursts of new star formation, when tidal forces stretched and ultimately destroyed the smaller galaxy's structure. It survived all of that. It emerged from cosmic violence unscathed, its quiet nuclear burning utterly indifferent to the gravitational chaos happening around it. While its galaxy was being torn apart, while its sibling stars were being flung into new orbits or absorbed into the growing Milky Way, Methuselah just kept converting hydrogen to helium, one fusion reaction at a time. The Gaia spacecraft has been revolutionary for understanding this history. By measuring the positions and velocities of millions of stars with extraordinary precision, Gaia has revealed the Milky Way's halo to be a graveyard of destroyed galaxies. Stars that seem randomly scattered actually have coherent motions when you look closely. They're moving together, following similar orbits, because they came from the same dwarf galaxy that was ripped apart billions of years ago. Methuselah's orbit suggests it might be part of one of these ancient merger events. Its velocity and trajectory place it in a group of stars that seem to share a common origin. If that's true, then we know not just when Methuselah formed, but where. In a small dwarf galaxy that no longer exists, consumed by the Milky Way's insatiable gravity, sometime in the first few billion years of cosmic history. There's a melancholy poetry to that, isn't there? This ancient star, burning patiently for 13 billion years, is the last witness to a galaxy that has been completely erased from existence. Its birthplace is gone. Its sibling stars are scattered or dead. It drifts through space carrying memories of a cosmic homeland that exists now only in the patterns of stellar motion that Gaia can detect. It's like finding a person who still speaks a language that has been extinct for millennia, a living connection to something that has otherwise vanished completely. But Methuselah is not unique. It's one member of a larger population of extremely old metal-poor stars that populate the Milky Way's halo. There are thousands of them, possibly tens of thousands, each one a fossil from the early universe. Most are too faint or too distant to study in as much detail as Methuselah, but they're there, scattered across the sky, each one carrying information about the conditions in the first billion years after the Big Bang. Some are even more metal-poor than Methuselah. A few stars have been found with iron abundances less than 100,000th of the Sun's, so pristine that they must have formed from gas enriched by only a single supernova. These stars are the holy grail of stellar archaeology. They're direct probes of individual population 3 explosions, carrying in their atmospheres the exact chemical signature of one specific primordial star's death. What all of these ancient stars tell us collectively is that the early universe was a busy place. Star formation began early and proceeded efficiently. Chemical enrichment was rapid. Small galaxies formed quickly and began merging almost immediately. The universe wasted no time in building complexity. And yet, despite all this rapid evolution, despite all the violence and change and transformation that characterized the early universe, despite galaxy collisions and supernovae and all the cosmic drama you could imagine, Methuselah survived. It formed in the chaos of cosmic dawn and simply kept burning, outlasting its more massive siblings, outlasting the galaxy that birthed it, outlasting almost everything except the universe itself. There's something profoundly humbling about that. We live in an era where stars like the Sun are commonplace, where heavy elements are abundant, where planets and life and complexity are possible because of billions of years of stellar nucleosynthesis. But Methuselah remembers a time before all of that, a time when the universe was chemically simple, when most stars were giants that burned and died quickly, when galaxies were just beginning to take shape. It's a bridge between cosmic dawn and the present day, a continuous thread connecting the infant universe to the mature cosmos we inhabit now. And it's still burning, still here, still patient after all this time. Looking at Methuselah is looking at history. Not human history, not even Earth's history, but cosmic history. The deep time that makes all our terrestrial timelines seem like brief flickers. The star tells us that even in the vast sweep of cosmic evolution, even across 13 billion years of change and transformation, some things endure. Not because they're special or protected or chosen, but simply because they were built to last. Built from the right materials, with the right mass in the right circumstances, and then left alone to do what stars do: burn. Studying these ultra-metal-poor stars is like reading individual pages from the universe's early history. Each star's chemical composition tells you something about the supernova that enriched the gas it formed from. The ratios of different elements, oxygen to magnesium, silicon to iron, depend on the mass of the exploding star and the details of the explosion mechanism. By analyzing these ratios in enough ancient stars, astronomers can reconstruct what the first generation of stars was actually like. And what they're finding is fascinating. The chemical patterns suggest that population 3 stars came in a range of masses, not just the supermassive giants that some early models predicted. Some were moderate in size, producing supernovae with different chemical signatures. The early universe appears to have been more diverse in its stellar populations than we initially thought. Methuselah contributes to this picture. Its specific mix of elements, slightly enhanced in what astronomers call alpha elements like oxygen and magnesium, relative to iron, suggest it formed from gas enriched by core collapse supernovae from massive stars. This is exactly the signature you'd expect from population 3 enrichment, where the first stars exploded and scattered their fusion products into the surrounding gas, seeding the next generation. The Methuselah paradox began as a problem with one star's age, but along the way to resolving it, we've learned something more profound about the nature of cosmological measurement itself, about what it means to know something with precision, about the intricate web of dependencies that connects every measurement to every other measurement, and how easily that web can produce results that seem impossible until you carefully untangle the threads. Let's step back and consider what precision cosmology actually means. We live in an era where we can measure the age of the universe to within about 20 million years, an uncertainty of less than 0.2%. That's extraordinary. That's like measuring the distance from New York to Los Angeles to within about 6 miles. We can do this because we have exquisite data from satellites studying the cosmic microwave background, because we have theoretical models that describe cosmic expansion with elegant mathematical precision, because centuries of careful work have given us the tools to decode ancient light. But precision is not the same as accuracy. You can measure something very precisely and still be systematically wrong. The Methuselah paradox reminded us of this distinction in a particularly stark way. When astronomers first calculated Methuselah's age, they used the best available data and the best available models. The distance came from Hubble, one of humanity's most sophisticated instruments. The stellar models incorporated decades of research into how stars evolve. The measurements were precise, small error bars, high confidence, and yet the answer was wrong, not wildly wrong, not catastrophically wrong, but wrong enough to matter, off by about 1 billion years, which is enormous when you're trying to fit a star into a 13.8 billion-year-old universe. The problem wasn't carelessness, it was the accumulation of small systematic errors, each one too subtle to notice individually, but compounding into a significant bias. Distance measurements that were slightly off, opacity models that didn't quite account for low metallicity, helium abundances assumed rather than measured, each small uncertainty pushing the age estimate in the same direction, upward, until the final number broke through the universe's boundary and became impossible. This is the challenge of precision cosmology. You're building a tower of inferences, each layer resting on the ones below, each carrying its own uncertainty. And sometimes those uncertainties align in unfortunate ways, all pushing your conclusion in the same direction, creating a systematic bias that's hard to detect until you step back and realize the final answer doesn't make sense. The resolution came through patience and refinement, better distance measurements from Gaia, improved stellar models accounting for low metallicity, more sophisticated three-dimensional atmosphere simulations, each correction small, but collectively shifting the age estimate downward by more than 1 billion years, bringing Methuselah back into alignment with cosmic history. This process, identifying the problem, tracing it back through layers of inference, refining each measurement and model, gradually converging on a more accurate answer. This is science at its best. Not dramatic revelations or sudden insights, but patient, methodical work that slowly closes the gap between what we measure and what actually is. And yet, even after all these corrections, there remains an underlying tension in cosmology that the Methuselah paradox highlighted but didn't resolve: the Hubble constant problem. The Hubble constant determines how fast the universe is expanding, and therefore how old it is. Measure the expansion rate one way, using the cosmic microwave background, and you get about 67 kilometers per second per megaparsec, which implies a universe 13.8 billion years old. Measure it another way, using supernovae and other local distance indicators, and you get about 73 kilometers per second per megaparsec, which implies a universe only 13 billion years old. Both measurements are sophisticated. Both have small quoted uncertainties. Both have been checked and rechecked by multiple independent teams, and they disagree by about 9%, which is far more than their individual uncertainties should allow. This is awkward. Not as awkward as having a star older than the universe, but still uncomfortable. It suggests that either one measurement method has a subtle systematic error we haven't identified, or our model of cosmic expansion is incomplete in some way, or there's new physics we don't understand affecting how the universe expands. The implications are significant. If the local measurements are correct, it could mean that dark energy, the mysterious force accelerating cosmic expansion, behaves differently than we thought. Or there might be additional components to the universe that we haven't accounted for. Or the universe's expansion history could be more complex than the simple models assume. If the CMB measurements are correct, it might mean that our understanding of local distance measurements has subtle problems. The cosmic distance ladder, the series of techniques we use to measure distances to farther and farther objects, rest on calibrations that could harbour small systematic errors. Or there might be something about how light travels through the universe that we don't fully understand. Some subtle effect that biases local measurements. Either way, something interesting is going on. The Hubble tension isn't going away with better data. If anything, it's becoming more pronounced as measurements improve. This suggests we're not just dealing with random errors that will average out with more observations. There's something systematic happening, and figuring out what it is could lead to new physics. The Methuselah paradox sits right in the middle of this tension. If the local measurements are correct and the universe is only 13 billion years old, then Methuselah at about 13 billion years is extraordinarily old but not impossible. It formed very early, within the first few 100 million years after the Big Bang, which is about as early as a population 2 star reasonably could form. The margins are tight but workable. If the CMB measurements are correct and the universe is 13.8 billion years old, then Methuselah is more comfortably ancient. It formed maybe 800 million years after the Big Bang, giving plenty of time for the first generation of stars to do their work first. The timeline is less squeezed. Either way, the refined age estimate for Methuselah, around 13 billion years, fits within the plausible range of universe ages. The paradox has dissolved, or at least transformed into a much milder tension that doesn't threaten the foundations of cosmology. But the Hubble constant disagreement remains, and it's possible that stellar ages like Methuselah's could eventually help resolve it. If we can measure the ages of enough ancient stars with sufficient precision, if we can map out the age distribution of the oldest stellar populations in the Milky Way and nearby galaxies, we gain an independent constraint on cosmic chronology. Stellar ages don't depend on the Hubble constant directly. They come from completely different physics, stellar evolution theory rather than cosmic expansion, so they provide an independent check. If very old stars consistently cluster around 12.5 billion years, that would support a younger universe and favour the local Hubble constant measurements. If they cluster around 13.5 billion years, that would support an older universe and favour the CMB measurements. Right now, we don't have enough precisely dated ancient stars to make this determination. Methuselah is one of the few that's close enough and bright enough to study in great detail, but projects like Gaia are changing that. As we measure distances to millions of stars with high precision, as spectroscopic surveys measure their compositions and temperatures, as stellar models continue to improve, we'll be able to determine accurate ages for larger samples of ancient stars. Give it another decade or two, and we might have a statistical distribution of ages for the oldest stars in the galaxy, and that distribution will tell us something about when star formation really began. how quickly the early universe assembled its first stellar populations, and potentially which measurements of the universe's age are more reliable. There's something beautiful about this, a paradox that initially seemed like a crisis. A star apparently older than the universe has evolved into a tool for understanding cosmic history more deeply. The careful work of resolving the paradox refined our stellar models, improved our distance measurements, and revealed subtle systematic errors that were affecting other calculations too. And now ancient stars like Methuselah might help resolve one of the biggest puzzles in cosmology. This is how science progresses, not through sudden revolutions that overturn everything we thought we knew, but through the patient accumulation of better data, more refined models, and deeper understanding. Anomalies like the Methuselah paradox aren't disasters, they're opportunities. Invitations to look more carefully, measure more precisely, think more clearly about what our measurements actually mean. The history of cosmology is filled with these moments, observations that didn't fit the prevailing models, measurements that seemed impossible, results that forced us to reconsider our assumptions. Sometimes they led to revolutionary discoveries, dark energy, dark matter, cosmic acceleration. Other times they led to refined understanding of more conventional physics, but always they pushed the field forward. The Methuselah paradox falls into the second category. It didn't overturn cosmology, but it did refine our understanding. It showed us where our measurements were vulnerable to systematic error. It revealed how small biases in multiple independent measurements could align to produce a dramatically wrong result. It demonstrated the importance of checking assumptions, of refining models, of always being willing to question your conclusions when they don't make sense. The paradox also taught us something about the nature of cosmic time itself. We talk about the universe being 13.8 billion years old as if that's a simple, straightforward fact. But it's not. It's a model-dependent inference derived from observations of the cosmic microwave background, combined with assumptions about how the universe has evolved since then. Change the assumptions slightly, adjust the parameters describing matter density, dark energy, spatial curvature, and the age changes. This doesn't mean the age is arbitrary or meaningless. The constraints are quite tight, but it does mean we should hold our numbers with appropriate humility. The universe is 13.8 billion years old according to our best current model, given our best current measurements, interpreted through our best current understanding of physics. All of those qualifiers matter. Methuselah reminded us that even our most precise measurements can harbour subtle errors, that models are approximations, however sophisticated they might be, that the universe is under no obligation to be as simple as our equations assume, and that sometimes the most valuable thing a measurement can do is disagree with our expectations, forcing us to look more carefully at what we think we know. There's also something philosophically interesting about the whole episode. For a brief moment in astronomical history, we had strong evidence for something logically impossible, a star older than time itself, not because the universe had broken its own rules, but because our measurements and models had conspired to produce an impossible result. This highlights the gap between reality and our knowledge of reality. The universe was doing what it always does, following physical laws that don't care about our measurements. Methuselah was 13 billion years old all along. The paradox existed entirely in our heads, in our calculations, in the small accumulated errors that pushed our age estimate too high. And yet, in a way, the paradox was real. It was a genuine problem that needed solving. The fact that it arose from measurement error rather than cosmic impossibility doesn't make it less interesting or less valuable. If anything, it makes it more interesting, because it reveals the subtle ways that uncertainty can accumulate and compound in complex systems. This is what makes cosmology both humbling and exhilarating. We're probing the fundamental nature of reality, the age of the universe, the fate of the cosmos, the structure of space and time, using instruments that are powerful but limited, models that are sophisticated but approximate, mathematics that is elegant but incomplete. Precision cosmology is an exercise in humility. We're trying to measure things across unimaginable distances and vast stretches of time using instruments that, however sophisticated, are still fundamentally limited. We're inferring properties we can never directly observe: the interior structure of stars, the expansion history of the universe, the composition of dark matter, from indirect evidence that always carries uncertainty. And yet we do it. We build better instruments, we refine our models, we check our assumptions, we find the errors, correct them, and measure again. Slowly, patiently, we close the gap between what we measure and what is. The universe is comprehensible. That's perhaps the most profound lesson from episodes like the Methuselah paradox. Reality follows rules that we can discover. When our measurements produce impossible results, it's not because reality is impossible. It's because we've made an error somewhere in our chain of inference. Find the error, correct it, and suddenly the impossible becomes possible again. Methuselah now fits comfortably within cosmic history. The star that seemed to break time has been reconciled with time. Not because the star changed, but because our understanding did. Because we measured more carefully, modelled more accurately, and thought more clearly about what our numbers actually meant. And the star continues burning, as it has for 13 billion years, utterly indifferent to the intellectual journey it sent us on. It doesn't care that it briefly appeared impossible. It doesn't know that its existence helped refine our understanding of stellar evolution, improved our distance measurement techniques, and might eventually contribute to resolving the Hubble constant tension. It just burns. Hydrogen to helium, fusion reaction by fusion reaction, patient and steady and eternal, or at least as close to eternal as anything in this universe can be. There's something quietly profound about that. The universe doesn't need us to understand it. It simply is. Stars burn, galaxies evolve, time flows forward, whether we measure it correctly or not. Our measurements, our models, our understanding, these are human constructions, attempts to map reality using the tools of mathematics and observation. Sometimes our maps are wrong, sometimes our measurements mislead us. Sometimes we convince ourselves of impossibilities because small errors conspired in unfortunate ways, but the territory remains. Reality persists, indifferent to our confusion, waiting patiently for us to draw better maps. And eventually, through care and patience, and the accumulated effort of thousands of people measuring and calculating and thinking, we do draw better maps. We do close the gap between what we think we know and what actually is. The Methuselah paradox is resolved. The star fits within time. The universe makes sense again. And somewhere, 190 light-years away, an ancient star continues its quiet work, converting matter into energy, turning hydrogen into helium, burning with the same patient intensity it has maintained for 13 billion years, yet unaware, unconcerned, enduring. Just a star doing what stars do. And perhaps the most important lesson from the Methuselah paradox is this: uncertainty is not weakness, it's honesty. Every time an astronomer publishes an age estimate with error bars, 13 billion years plus or minus 400 million, they're acknowledging the limitations of measurement. They're saying, this is what we know, and this is how sure we are. That uncertainty isn't a failure of the scientific method. It's the method working exactly as designed. The temptation is always to present results as more certain than they are, to round off the error bars, to downplay the uncertainties, to speak with confidence that exceeds what the data actually support. But science progresses not by pretending to know more than we do, but by being scrupulously honest about what we know and what we don't. The Methuselah paradox emerged precisely because astronomers were willing to report measurements honestly, even when those measurements seemed impossible. They could have quietly adjusted their numbers to make the problem go away. They could have expanded their error bars until the star's age and the universe's age barely overlapped and called it close enough. But they didn't. They published the uncomfortable result and let the community wrestle with it. So, we've followed an ancient star across 13 billion years. We've traced a paradox from impossibility to resolution. We've seen how measurement error can produce cosmic confusion and how patience and precision can restore clarity. And now we come back to the present, back to the star that's still there, still burning, 190 light-years away. Methuselah hasn't changed, still converting hydrogen to helium as it has been for 13 billion years, still drifting through the Milky Way on its lonely orbit, not older than the universe, just older than almost everything else. Patient, enduring, indifferent to the paradox it briefly created in our calculations. If you've enjoyed this journey through cosmic time tonight, if these explorations help you appreciate the patience required to understand deep history, don't forget to subscribe to the Sleepy Astronomer. There are more cosmic mysteries to explore together, more paradoxes to untangle, more ancient light to decode as we drift through the universe learning its secrets. And if this particular mystery resonated with you, a like helps others discover these late-night wanderings through space and time. Thank you for wandering through impossible ages with me, for following one star's journey from paradox to clarity. This is the Sleepy Astronomer, wishing you clear skies, peaceful dreams, and the quiet comfort of living in a universe old enough to produce wonder. Good night and sleep well beneath ancient starlight.